Okay. So 2 minutes until start, and as organizers, we are really glad and proud to have this session organized in collaboration with network NoR CEL, the network of researchers dedicated to investigation of the origins of the life. And we have special guest chair, Professor Martin Dominic. Professor Martin Dominic is reader at the School of Physics of the Astronomy at the University of St Andrews, Scotland, UK. His research focuses on applications of the gravitational microlensing effect, and in particular on its potential for studying planets orbiting stars other than Sun. So Martin, you are more than welcome to take over the conference and lead this session.
Can you see my PowerPoint?
Yes, Sohan, we can see your presentation. Let me thank Angelica for the introduction and the very kind invitation. And now we shouldn't hesitate to start our program, and let's see whether we can transcend some boundaries. And the first speaker of this session is Sohan Jita, who will talk about some of the basic building blocks of life. Sohan, the floor is yours.
Okay, thank you very much. Thank you, Angelica. It's a pleasure to see you and to talk to you again. And of course, we represent a network of researchers on the chemical evolution of life. A bit of announcement here that we will be hosting our virtual conference in March 21. And the date hasn't been decided. As soon as it has, we will let you know. And if you've got anything to say on this matter of chemical evolution of life, please join us. So today, I'm not going to talk about astrochemistry, the whole field. I'm just going to confine myself to building blocks of life. How do I remove this strip on the side? Oh, right. So I'm just simply going to talk about building blocks of life, molecules, that is. So what is astrochemistry? Astrochemistry is simply that study of formation of molecules in space, as well as under simulated space conditions in laboratory setting. But what we need to do is to find out where else could these molecules have been made other than astrochemistry and in space. Well, some people might have to correct me at a later date, but there are some papers out there that where you can make molecules between boundaries of a dense and a less dense layer, so that within that layer, some molecules will be trapped, and these trapped molecules would be irradiated by say, Saturn's magnetosphere would impinge some high energy particle onto Titan's atmosphere. So that was one example. And of course, people think that Titan was or is the early representation of the Earth, very early Earth representation. Next, what you can do is to make some molecule in the primordial planetary atmosphere. And you would use lightning, the type that is produced in the present day volcanic activities or plumes. So the one that's sort of shown here, this type of lightning is much more stronger, much more intense compared to the one that is found in over the desert environment. Next, you can actually make some molecules in small puddles of water at the foothills of volcanoes. That is to say, you'd have a lava column on one side, about half a kilometer away from the volcano itself, there may well be holes in the ground where the hot gas and water would be seeping out. And this would make a nice environment for getting some serious chemistry going. Of course, some people are doing work in that in this field, in small puddles of water by the volcanoes. You can also make some molecules on the early shores of planetary planets. Like, for example, Moon was much closer to the Earth, and thereby the ebb and flow of tides were much stronger and more frequent. And it was, I think it was something like 6 hourly that in, out, the tides are going. So this wetting and drying process is believed that could form the necessary molecules for the life's origin. And then there is the question of hydrothermal vents. I'm a little bit skeptical. I had quite a lot of discussion with people who promote hydrothermal vents. The reason behind it is that if the Earth was about 300 million years old when the plate tectonics were made, but you not only plate tectonics are necessary, but also you need other like, for example, you need clays, particular type of clays. Marillonite is one, for example. These types of clays are necessary for the formation of life. And of course, that is the cornerstone of alkaline hydrothermal vents. But it's up to you to make some sense of it, whether they were important at the time or not. But I personally don't think so, but I thought I'd say it anyway. And then there are some people who have done work with impactors as well, where comets hits the Earth, and as they traverse through the atmosphere, the comets heats up, or the meteorites or the asteroids, they heat up as soon as they hit the Earth. They unleash very extreme heated environment, and it is believed that the molecule break bonds and reform, and that could also have some bearing in the formation of molecules on Earth. And I'm here to talk about astrochemistry, so I'll get on with that. So dark molecular clouds are thought to be the chemical factories in space, especially during the early planetary systems. And Horsehead Nebula is one such example where this area has been studied vastly by over 1,000 papers. And these structures are made from 80% dihydrogen, 19% helium, and 1% or less elements and other molecules. Of course, they're dark because they also contain 1 interstellar dust particle for every million per cubic centimeter. And the pressure in these environments is something like 10 to the minus 13 millibar, and the temperature varies anything from 10 to 50 K. Type of chemistry included in these places is photolysis, radiolysis, and thermal processing. I forgot to mention they also are impinged by both high energy particle radiation as well as UV light. So let's talk about evidence for these molecules being in space. So we have four ways of doing this. First, Murchison meteorite, for example, that is not just that. I mean, all carbonation meteorite contains some organic molecules, like in this burgundy spot here, the one that I'm pointing out. If you were to drill it out, grind it, and then add some acetone, lo and behold, you'll extract some organic molecules, and then which you can identify using various techniques like HPLC. You can also send return mission to space, like this one, Stardust spacecraft that was sent in 1999. It brought back a sample from by visiting Wild or Wild 2 comet. And what this particular spacecraft did was to pass through the comet's tail with its gel, and the gel captured some of the particles coming off the comet as it was being heated by the solar radiation as it was hurtling towards to go around the sun. Of course, you can also use, by examining these gels, you would find they found glycine. Glycine is one of the 20 amino acids, the very simple one, very important one, and they isolated that. Of course, you can also use this antenna like the one at the Jodrell Bank near Manchester in the UK. And what these antennas do, they can pick up radiation, especially in the infrared range, coming from space, especially from the dark molecular clouds, like the Horsehead Nebula. What actually happens in molecules within the dark molecular clouds, they actually vibrate. And there are various different types of vibrations. Just to give you one example, when molecule absorbs a energy from a local star, the bonds expand, but as the bond relaxes to its ground state, it emits radiation, infrared radiation, and carbon dioxide, for example, have these wave numbers. So if Jodrell Bank were to be actually tuned to receive this kind of frequencies, then you're home and dry. Then you would actually get a trace like the one that where my cursor is. And these are the type of molecules that have been identified. This is one such trace. Of course, people have now since improved techniques since they were first detected, I think, back in 1932. And then also you can carry out the experiments in laboratory simulated experiments to tally with what you see, what you observe in space. And so what I'm going to do is to say something about molecular, something about the interstellar dust particles. These are very, very important for solid phase chemistry. And the other chemistry is gas phase chemistry. And I'm not going to talk about gas phase chemistry, but only confine myself to solid phase one, because that's my expertise. In any case, I fail to understand how a molecule, when the pressure is low, it's something like 10 to the minus 13 millibars in such structures as Horsehead Nebula, the molecules are far apart. I don't understand how they would actually bump into one another for the gas phase chemistry to take place. But anyway, let's get back to the point. Point is that the IDPs are 80% silicate and 20% carbonaceous. And the good thing about these is that you can see these convoluted areas in this. If you were to open these out, convolutions, and spread them out, you would find that it's the size of a football pitch. Oh, by the way, the size of these interstellar dust particles is less than 0.1 micrometer. And the only last point I got to say in this respect is that without this interstellar dust particle, it would not be possible to make molecular hydrogen, because when you combine two hydrogen atoms, the level of energy generated is enormous, and as soon as you get that dihydrogen being made, it splits apart again. But what the interstellar dust particle does is to take that heat away. It's called three-body reaction. And to date, these are the top 10 molecules found in space. And it's from Rouse, 2001. And they are from protostars and comets. And these numbers, these from 15 downward, for example, in protostars, they're relative to 100%, which is water. Water is thought to be, universe is full of water. Take my word for it. But anyway, I'm not going to talk about, sorry, I have to go back. What I got to do is that these molecules, I will visit them, remind you why they're important, how they got to be important later on. But I will not, ammonia, oxygen, and OCS, carbonyl sulfide, will not be said anything more about it. But anyway, these are the type of apparatus you would use. Due to the time, I can't talk about it, I won't talk about it. And Martin is looking after my time. Anyway, on the right-hand side panel, you will find that if you take inorganic ammonia and inorganic carbon dioxide and make some astrophysical ice with it by chucking it at a target made from zinc selenide in a vacuum of 10 to the minus 9 millibars, what that actually means, and you set your FDIR spectrometer to measure in real time within a few seconds of irradiating the ice, which is on the zinc selenide. Radiating the ice, it starts to form a bit of a chemistry here. So you formed OCN, cyanate, which is organic molecule. And this was done at 1 keV at electrons at 30K temperature being. And if you look at the left-hand side panel, this is using inorganic ammonia, organic methanol, again using the same energy, electron energy, and same temperature. You find that there's a rich chemistry taking place here. I forgot to mention in both of these, black traces represent no radiation, that is pre-radiation, and red trace represents the post-radiation. In this left-hand side panel means that it had been irradiated for at least 15 minutes. And you can see one of the important radicals. This is hydroxymethyl primary alcohol radical, really, really reactive stuff there. The type of carbon chemistry that takes place is, as I said, mentioned earlier on, photolysis, you carried out by electromagnetic radiation like the UV light, and also you've got radiolysis, and these involves all of these electrons. Oh, by the way, it doesn't stop here. You can have carbon, you can have any particle, ionic or atomic particle. So as long as they're hurtling towards these IDPs, they will carry out some bond breaking and reorganization in order to form a molecule. Thermal processing, I'll have to come back in a bit. Let's talk about photolysis. Excuse me. Let's talk about photolysis. So if you were to break a stubborn bond like this, like the nitrogen bond, what you get is nitrogen, atomic nitrogen and atomic nitrogen. They're identical. Therefore, we would call this homolytic reaction, and they would be called free radical. Free radicals are different from other radicals. These are called ions. Ions are formed when, for for example, water is irradiated at 4.4 electron volt. You get hydrogen ion and you get hydroxyl ion. And this would be, because they're different, this would be called electrolytic. I use the word stubborn for nitrogen, meaning that this energy is high, 10 to the 0.2 electron volts. And to give you an example, that methyl cyanide can be irradiated by UV light, but it could also be formed as well. Formed from methanol in the presence of HV, the UV light, and what you get is methyl ion here, hydroxyl ion, and you take this methyl ion, add to it some hydrogen cyanide, lo and behold, you get this particular radical here. And you've got HV, I've got HV written here. That's because this is exothermic reaction. It gives out energy. Using, again, dissociative recombination with the one electron, you find that you can make methyl cyanide and atomic hydrogen. But now that we formed a methyl cyanide, it could also be broken down, which I will talk to you about a little bit later on. But let's move on to radiolysis. So what we can do is, for example, break carbon dioxide with high energy particles into carbon monoxide and atomic hydrogen, oxygen. When you get two atomic oxygen together, you make molecular or dioxygen. But we did not detect dihydrogen because we didn't have the apparatus to do so, but other scientists have done, like Gerard Kynes, he has done it. And we observed carbon dioxide coming off at 2140 cm minus wave number. Similarly, you can break ammonia into NH2, and then you take the NH2, combine it with the, obviously this is happening same place on top of zinc selenide target. So it would form HNC cyanic acid, HNC or high cyanic acid. It could be observed at 2255 cm minus 1, but we didn't do it. We didn't see it. But what we saw was that we saw ammonium ion, which was at 1498, and OCN at 2165. So what we think happened was that cyanic acid in the presence of ammonia, because we are irradiating ammonia, remembering that we're irradiating ammonia, ammonia and carbon dioxide here. So basically what's happened is that it breaks down into, it forms this radical, this zwitterion, and then breaks down into ammonia and OCN, as I said. All right, okay. Let's explain a little bit differently. This graph shows from 0 to 5, 8, 17, 18 minutes, 58 minutes of irradiation. If you look at this line here, these peaks are increasing. These peaks are increasing. And at 17 minutes, it reaches the highest peak. At 17 minutes, the OCN, this peak is for OCN, and this peak is for carbon monoxide. But if you look at the carbon monoxide, they're increasing all the time. Again, what actually happens is this, that after a while of irradiation, 17 minutes of irradiation, the OCN starts to break down. That's why you got this pink curve here. It's below the 17-minute curve. And you follow it around and you find that the carbon monoxide is increasing. So you know that this destruction of ocean is taking place at the same time it is being made. Okay, let's talk about a little bit about the thermal processing. What actually happens is that this is a cartoon representation of this type of interstellar dust particle here. Space is cold, water is very, very sticky, and it sticks to anything very, very easily. That is, it sticks to interstellar dust particle. Onto you get absorption of various molecules like methane, like ammonium, and others. These are just a few of them. There's many, many others. And what happens is that they get irradiated by electromagnetic radiation, like, for example, represented here. And then you get the particle radiation impinging onto it as well. And of course, the process breaks the bond. The process breaks the bond of these chemicals, be it organic, be it inorganic. But if there is a cause for the interstellar dust particle to warm up, what actually happens is that these radicals within the icy mantle becomes mobile, and they combine with one another to form new molecule, new type of molecule. It may well be formic acid, for example, or formaldehyde. There are others as well, like formides, you know. So just to tell you that other than the major differences that are compared and contrasted here, the major difference between a UV photon and the energetic particle is that generally UV light it doesn't penetrate deeper into the ice. It sort of stays on the surface, whereas the energetic particle tend to go deeper into the ice. And also it knocks out electrons from water molecule, maybe perhaps other organic or inorganic molecules that are mixed up in that ice. This knocking of the electron causes secondary reactions, and it is this secondary electron that does a lot of the chemistry as well as the direct effect of these impinging particles. So that's the major difference I wanted to draw your attention to. One more difference is this. So you'd have deep at the heart of dark molecular matter. Sorry?
Just a moment, please. Please put Professor Istvan Vince into attendance because of the noise. Thank you.
Shall I continue?
Yes, continue, please.
Yes.
Yeah. Okay. So you have this deep in the heart of it. You have particle radiation at the surface. At the surface, you'd have sort of translucent areas where UV light would be more effective. To give you further examples, other things that are happening in the left-hand side panel, this time black represent temperature of 20 K, and the red represents temperature of 130 K. This is to show you that the ice that surrounds the interstellar dust particle is amorphous. It's a bit like a woolly, sort of a Christmassy sort of ice. Whereas the crystalline ice, which is represented by the red trace here, is crystalline, the type that you would find on your car's window screen during winter. And you can see these changes taking place. Can you see this bump here, this peak here? Now you've got two peaks here. There's no peak here, there's a peak here. That's just showing that there's some serious changes takes place when you warm up ice. but you have to do it slowly, by the way. And formamide, as mentioned earlier on, so if we were to make formamide, which we did from using inorganic, I use the word inorganic to remind you that this is inorganic and methanol is organic. So the mixture of two does produce formamide. Formamide, although if you were to observe it straight off on the solenoid target itself, as it will be formed, you may not be able to see it. The reason you wouldn't be able to see it, because it becomes visible when you do thermal processing, when you slowly increase the temperature at rate of perhaps 10 centigrade per every time per session. So change in temperature of 10 centigrade, you take a spectrum, you'd find that the formamide unveils itself in this respect at 160 K annealing. And this is the trace which is identical, well, very similar to this trace. This is done by a guy called Khanna in 2002. But he's also shown this one here. And what they did was they cooled it back. They cooled it back to its original 20 K temperature, and they kind of retained its original peaks.
Johan, you're about to run out of time.
Well, I've got a lot to say. Well, anyway, the point is that you can make many different types of, I'm coming to a conclusion. Well, there's a lot of, did you tell me 5 minutes gone by the way?
Yeah.
Oh, I didn't hear it. But anyway, so you have, you can form all these different types of molecules. Two of the important ones are cyanide, cyanoacetylene, and cyanide. Remember those. So if you use cyanoacetylene and cyanide, what you get is cytosine formed. If you take hydrogen cyanide, mix it with ammonium and heat it, and you get adenine being formed. These two are nuclear bases used in, I'm coming to an end, Martin, within a couple of minutes. These two are bases in contemporary biology. And these are the experiments done by radiolysis of methanol, photolysis of methanol, and coma, the Ferris's coma detection molecules in a coma. And these are Rouse 2001 experiment report, which I showed you earlier on. So you can see that it's rich, that whatever method you use, wherever you look for, the space chemistry is rich, has a rich tapestry of chemical molecules. Anyway, if you were to use lightning, for example, Uri Miller type of experiment, and you find that he made in 1953 these dozen or so amino acids. And of course, also you people have found dozen or so same number of amino acids in Murchison meteorite. These 6 are found in the contemporary biology. This was taken from Gilmore 2003, just to tell you that space is rich in this is my last slide. Space is rich in chemistry. And of course, this is taken from a guy called Cooper 2011, which means that all of these chemicals have been found in meteorite, like the one that I mentioned, Murchison meteorite. All of these chemicals mentioned here, they're small, and they're used in pathways and cycles in chemistry, by life, contemporary life forms. And just to say that they were delivered onto the Earth. Whole of the shebang was delivered onto Earth between 4.3 to 4 billion years ago. And this is to remind you that space chemistry does form the necessary, that's the word I want to use, necessary molecule, life's molecules. I've shown it to you in terms of molecules for the amino acids and for the cycles and pathways. Okay, thank you very much. I'm sorry if I took over time.
Thank you, Sohan. Just a reminder, if you want to ask questions, you can either use the raise hand feature, which is within the participants dialog, or you can just type something in the chat. So is there any very urgent question to Sohan that can't wait until the break? Or alternatively, you could also type something in the chat and then Sohan can answer that directly in the chat. Somebody with a question? Let me ask one. Sohan, what would you consider a most intriguing question in this context?
I'm sorry?
What would you consider a most intriguing question in this context?
Most intriguing question. The question would be, where were the molecules made? You know, I've told you several places. Of them, there must be one ahead of every other question, every other molecule, you know, place where it was rich in chemistry, might say. I don't know.
Okay. Thank you again, Sohan.
All right, thanks, Martin.
And let's move on to our next speaker, who is Branislav Vukotic, and who is going to talk about galactic habitability.
Hello, can you hear me?
Yes, we can hear you well.
Okay.
There should be an alarm sounding after 25 minutes. Yes, we see your slides coming through.
Okay, so it's fine, I can start. Okay.
Yes, you're ready to go.
Okay, thank you. And thanks everybody for attending this conference. I'm going to talk about models of galactic habitability and the research we did here at the Astronomical Observatory in Belgrade in the last 15 years. And how can we improve them by including the stellar motion into them and why it's need to be done. So first, a few words about the importance of galactic habitability studies. Essentially, matter in the universe is primarily organized into galaxies, and we can say that the overall evolution of matter in the universe is connected with life and life in the solar system, because solar system is integral part of the universe. So galaxies would be not just the focal points for studies of the evolution of matter in the universe, but also for studying the phenomenon of life and answering the questions about origins of life and life evolution. If we extrapolate it in the future, it can give us also potential to answer the questions about humanity's prospects for spreading out in the galaxy or contacting other civilizations. That's something I will mention about later with one of our models that we developed here. So it started with the discovery of exoplanets we saw the last year's Nobel Prize in Physics for 2019 for discovery of first exoplanet with a radial velocity method. We see here the scientists who did that and their instrument called spectrograph called LOD. Now, later on, many discoveries were also made with the transit method, and we saw that there are many planets like Earth out there, and also from the previous lecture, we have seen that there are many organics which are building blocks of life in the solar system and in the outer universe. So we can think that life, at least simple life, should be a widespread phenomenon in the universe, and that there should be many Earth-like planets out there with at least simple life, if not also complex life as well. So essentially, as the interest in studies of exoplanets and life on exoplanets builds up, it also saw the growing interest in galactic habitability studies. And now the basis for the first galactic habitability models was essentially the model of stellar habitability or circumstellar habitable zone. So given the geometry of the problem, we see that we have some annular region of space where the temperature is such that the planet feels most comfortable to have a life as integral part of it. For example, if we set the Earth-like conditions and water in a liquid state, the temperatures around 0 degrees would define the circumstellar habitable zone. If we assume that planet radiates away like a black body, the energy that it receives from the sun. Of course, over the years, these models got more and more complicated, including various levels, such as including the cloud covers or greenhouse effects, etc. And also they get more complex when you consider binary stellar systems. So then it's not just as simple as in the case of single stars. So based on these models, the first models of galactic habitability appear. So the very first one was in this paper by Guillermo Gonzalez. Some 3 years later, we got another one, and all of these models from this page, they essentially were relying on metallicity. As the models on stellar habitability relied on stellar flux and distance from the star, these models relied on are based on building blocks to form Earth-like planets. That is the sufficient metallicity to form planets. So they should allow for enough time to metallicity in the galactic disk to build up to form planets. These ones from the first row were very conservative, and their results are that most of the habitable planets should lie at some galactocentric distances that are similar to the one that we found solar system today. The two from the bottom row essentially give somewhat different results. So instead of having the ring-like annulus centered on the galactic center, the one from this paper gave a little more chances for habitability near the galactic center because from the increased number of stars there. And this one concluded essentially that whole of the galactic disk might be habitable, so that we don't have much reasons to consider the galactic habitability zone being a ring-like shape that spreads outward as the metallicity builds up. So these models factor in metallicity, star formation rates, and dangers from supernova, essentially. And depending on how they included these factors in their models, they got different results. So in this first decade, no census was made on how the galactic habitability should look like. We use such a simplified models to make a simple model of our own and test the relevant timescales for the development of complex life and galactic civilizations in our galaxy. So all of the models from the previous slide, like this one, are that do not include motion of stars. So they are models that are based on solving the equations of relevant parameters, and probably some of them populate the stars, the disk of the galaxies with stars, but they don't include stellar motions in them. So we did here the same. We make the galactic habitable zone as a ring in 2D, which consists of a grid of cells, and each of that cells develop towards increasing life complexity, denoted by these colors here. And these structures are the beams of highly radiation intensive events such as gamma ray bursts, and we also model supernova, but they're like these white dots here. So essentially, they can hinder the development of life in one point of the grid, and we factor in various timescales that are relevant for the development of life from simple to complex one. And here we examine how these timescales that are related to catastrophic events, for example, nuclear catastrophe or something that destroys a civilization, or resource depletion, how they compared against possible colonization timescales. These here are the logarithmic scales of time in years. So by examining this huge parameter space, we find this simple model quite handy, because we end up at the end with a bunch of clusters of the cells with highest complexity, and their total number is shown here on this color-coded plot. And the results are published in this work, Jošović et al. So we can see here that this parameter space shows some part with non-linear behavior. So here we don't have a smooth transition, but when we see this lightly colored median here, it goes quite fast to the places where we have a really low number of developed civilizations. So as the time of colonization goes up, this number goes down, and as the time of catastrophism goes up, the number of civilizations increased. But here on this side of the graph, it flats out, while here it shows a big dip. So we can get an idea of what are the possible timescales and what are the critical parts of the parameter space. So we can see which of them we can use to make more complex model that will include the and factor in the dynamics of stars. And why the motion of stars is important, we can see here in the past decade, it became clear that it is really important for the various aspects of galactic evolution studies, not just the studies of galactic habitability, that are essentially are building up on the knowledge we get from the studies on galactic evolution. This plot is from this work in 2012, and it shows the number of stars, not the stars, but the number of particles from an n-body simulation of a galaxy that are between 7 and 9 kiloparsecs at the end of the simulation. And here we can see the fraction of their birth radius. So we can see that roughly 50% of the stars that are between 7 and 9 kiloparsecs are not do not originate from that part of the galaxy, but most of them originate from inner parts of the galactic disk. Probably it might be the case with our sun also. So we essentially have a flux of stars that goes from inner to outer parts of the galaxy. Some of the stars go in opposite direction, but these radial migrations show that we should not have much confidence in static models of galactic habitability. So we try to perform a habitability analysis of n-body simulation of an isolated galaxy, which is very similar to the Milky Way in its setup. And when we factored in the parameters that are relevant for the solar environment, such as the star formation rate and the stellar density, we constructed the model in such a way that if the star formation rate is higher than in the solar neighborhood, we didn't consider these sites to be habitable. So we can see here, after some 5 billion years, the habitability starts to appear, the habitable site starts to appear between 10 and 15 kiloparsecs from the galactic center, and they stay on this galactocentric radius. Just what is changed is the buildup of particles over time, including eventually also the lobes of this distribution, the tails of this distribution, which spreads towards the inner and outer part of the galactic disk. So instead of having inner parts of the galactic disk or solar galactocentric distances, the most habitable parts of the galactic disk, due to the diffusion of the stellar component towards the outer parts of the disk, we see the increased habitability of the outer parts of the galactic disk. Also, this is here galaxy in isolation, but most galaxies are not isolated, like also our Milky Way. It interacts with its surrounding galaxies. So this should be also considered when models of habitability are made. So in the next study, we have the analysis from the CLUES simulation, which is a simulation of the local universe. And here we can see the group of galaxies that is familiar to the looks similar to the local group Milky Way and its surrounding galaxies. The central galaxy should be the Milky Way. So we can see here how the how the habitability evolves with time, and although because these are the projections of the number of habitable planets, so that's why the centers of the galaxies are the most habitable one, because these are the projections. But the paper states that the outer parts of the galaxy is also the most habitable one. And what we can see here, as time passes from these upper panels to the panels below, the habitable sites can see in further away from the center of the galaxies, and they're more mixed with the surrounding galaxies. Also, we can, because of the interaction of these galaxies. So probably the problem of habitability transcends the boundary of a single galaxy and should be also considered in the intergalactic space. These dwarf galaxies that surround the main galaxies are also showing significant peaks in a number of habitable sites. What next we did is in the work by Stojkovic et al., we analyzed the galaxies from Illustris cosmological simulation, and this is the number of galaxies given their mass and metallicity, and we found this interesting feature here of galaxies, which would be the small galaxies in mass and with higher metallicity, significantly than the other part of this plot. So we performed the habitability calculation from these parameters here based on metallicity and power law exponent for building up, for probability of building up Earth-like planets based on metallicity. And we normalize it to the number of planets we find in the Milky Way with the same calculation. So here we have a plot of habitability of this part of the parameter space where these galaxies are shown. And we can see that the galaxies with larger mass naturally have more habitable planets, but since they are also a bit higher in metallicity, this also can contribute to their habitability. So this is something that we plan to work on further and investigate in another set of simulations from this project, how this part of the parameter space will look like, and how it will shown in terms of habitability. Okay, so we're near the end of this talk, and we can see here plots of orbits of stars, which can help us to include dynamics of stars in the models of galactic habitability, because simulations of isolated galaxies, and especially cosmological simulations, they have a mass resolution of about a stellar cluster, so 10 to 4 or 10 to 5 solar mass is the mass of one stellar particle in the simulation. So if you want to realistically see what happens on a stellar level and how it affects habitability, we need to find a way to make our models on a stellar level motion, but also to include the effects of galactic evolution and interaction of galaxies. And one way to do that is to use the potential from cosmological simulations and make its analytic approximation, and then see how test particles behave in such a potential, and run these test particles through this potential in large numbers and see how the statistics of their orbits and how close they get to each other, because this affects the stability of the planetary systems, and how often they pass through the radiation hazardous environments such as supernova explosions, and also through galactic or spiral arm patterns. So these here are from work by our colleague Milan Stojanovic. These are two stars from the thin disk of the galaxy and their orbits. So you can see how they behave in a plane of the galaxy and in the vertical coordinate. And we plan to use this synthetic approach to improve our further models and get better insight in what's going on in the field of galactic habitability. So that would be all. Okay, I'll be happy to hear and answer your questions.
Okay, thank you, Branislav. Are there any questions? Remember, if you don't have any questions right now, you can always use the chat. Branislav, similar question to you. What would you consider a most intriguing question in this context?
I thought about it when you asked the question the first time. And I find it hard to put in this half an hour in this presentation the hypothesis of panspermia and the ability of life to survive or the building blocks of life to survive the travel between various planetary systems and maybe the galaxies. So it would also be one of the important parts of these kind of models to also consider these effects.
Good.
Professor Vince has a question. He's an attendee. Professor?
Yes, thank you. I have a question. How it looks like the function in between the habitability and the metallicity? It is a linear or other one? How it looks like?
It's usually a power law function because the planets, the number of planets we can expect looks like a power law when it's calculated from metallicity.
Okay, and it depends on?
Metallicity is measured from observations or its input from the models of chemical evolution.
Okay.
And it depends, like really simple form, like the metallicity on some exponent, like 0.1, 0.5 or something like that.
And it is, how to say, it is a fixed number, or you try to?
Well, we try to vary it. For example, you can see here in this model, it's varied from 0 to 1. And for really large planets, you have a different kind of, it's also a power law, but it's a fixed power law. I don't know exactly, but it's like it's 10 to the value of metallicity for forming Jupiters.
I see.
Use it from some other.
Okay, thank you.
Are there any other questions? If this is not the case, then let me thank Branislav again. And we then move on to our next speaker, who is Alexandra Nina. There we go.
Okay. Hello, everybody. Can you hear me?
Yes, we can hear you well.
Okay. In this presentation, I would like to present you our recent research of the lower ionosphere related to periods around the earthquakes and application of this research in modeling of satellite signals. Before I start with the talk, I would like to say that this research is a result of collaboration. Several people from science from Serbia, Italy, and Russia. I'm from the Institute of Physics, Belgrade. Vladimir Čadež and Luka Popović are from the Astronomical Observatory, Milan Radovanović from Geographical Institute Jovan Cvijić, Srđan Mitrović from Novelik, and Oleg Odalović and Miljana Todorović-Drakul from the Department of Geodesy and Geoinformatics from Faculty of Civil Engineering. From Italy, we collaborate with Giovanni Nico and Pier Francesco Biagi, and from Russia with Sergei Pulinets from Space Research Institute of Russian Academy of Science. In this talk, I will present two studies related to disturbances in a period around earthquakes and during a solar X-ray flare influence. In the first part, I will present you our analysis of observational data in order to find a possible connection between an earthquake and changes in electrical properties of the lower ionosphere. And in the second part, I will present a research of influence of the intensive perturbed ionospheric D region on satellite signals used in Earth observations and positioning. Here, I would like first to explain our experimental setup and our observations, namely, in the Institute of Physics, Belgrade, we have a receiver station for very low and low frequency radio waves. These waves are in domain of frequencies between 3 and 30 kilohertz and 30 and 300 kilohertz. We monitor the lower ionosphere, which is at altitude somewhere between 50-60 kilometers and about 90 kilometers. Here you can see how these waves propagate. You can see transmitter and so-called sky waves, namely these waves which propagate very close to the Earth's surface very quickly attenuate, and practically we have only sky waves in this so-called Earth ionosphere wavegate. These waves reflect from the ionosphere, come back to the Earth's surface, again reflect to ionosphere, and these reflections repeat in Talasovod, in wavegate, and they can propagate several thousand kilometers. Global setup for this technology of lower ionosphere monitoring is built from numerous worldwide located transmitters and receivers. In this map, you can see the most important transmitters, and also there are many receivers, and one receiver station is in Belgrade. Receivers can have a possibility to continuously monitor these waves, and they can monitor several, practically in the same time several signals with time resolution that is lower than 1 second. That is very important because we can detect events, unpredictable events, and we also can detect events whose lasting is lower than 1 second. There are many processes which induce changes in ionosphere, actually that induce disturbances in ionosphere. They are from the different Earth's layers and also from the outer space. We have earthquakes, tropical cyclones, lightnings, and volcano lightnings. The most important is solar radiations, and also we have reaction on gamma radiation, for example, gamma ray bursts. On the other side, state in the ionosphere is very important for propagation of electromagnetic signals. General electromagnetic waves for us, it was important satellite signals that is used for Earth observation, positioning. Also, it is the state of the lower ionosphere is important for telecommunication. In the first part of this study, I will present you our recent research about lower ionospheric disturbances before the earthquakes. Namely, there are many studies which describes changes and disturbances in ionosphere before the earthquakes. If someone is interested in this topic, I can say that the book of Pulinets and Boyarchuk is very good for reading. And in the left side, you can see block diagram of ionospheric of seismo-ionospheric coupling model. I will not speak about this model. I want to say that we can see many processes like generation of acoustic and gravity waves, anomalies, electric field generation, and so on and so on. And the most important is that these disturbances are recorded in both in the upper and the lower ionosphere. Because we monitor lower ionosphere, of course, for us is the most important perturbation in the lower ionosphere. These perturbations are generally detected by VLF and LF radio signals. And in order to monitoring earthquake precursors, there are several networks in the world, in Russia, Japan, and in Europe. That is International Network for Frontier Research on Earthquake Precursors, or INFREP. Now I will say only that from the last year, Serbia, actually Institute of Physics Belgrade is included in this network. So when we look at papers related to VLF-LF signal disturbances before the earthquakes, we can see that the focus is on variation in amplitude and solar terminator. Here you can see an example of amplitude variation before a few days before earthquake. Here you can see wavelet transform. This is time of earthquakes, and here you can see changes in terminator time. What is terminator time? I will explain in this graph. Namely, here we can see time axis for 1 day, or actually for several days, and one can see that we have differences in nighttime amplitude and daytime amplitude. Nighttime amplitude is generally larger than daytime, and in the past between nighttime and daytime, we have one inverse peak in period of sunrise and sunset, and the time of that peak is practically terminator time. Here you can see that that Kobe earthquake was January 17, and that changes in terminator time are recorded a few days before the earthquake. So the conclusion is that we have detected changes a few days before the earthquake. I want to say that these studies are done for signals with resolution of about 1 minute. But when we wanted to analyze what happened in ionosphere under Serbia in period of Kraljevo earthquake occurred 3rd November, on 3rd November 2010, we used data with time resolution of 0.1 seconds. So we have more data for analysis, and but we didn't file changes in the terminator time and some visible changes in amplitude. Because actually we find some changes, but when we compare them with changes during the year before, we can see that similar changes are also detected. However, we find one changes in amplitude noise. In this graph, you can see amplitude, and it is visible that less than 1 hour before the earthquake, we have significantly reduced in the noise amplitude. Question was, have a new type of earthquake precursor, because we didn't find this property in literature, and that was motivation for us to investigate this phenomenon. Generally speaking, this investigation is still in progress, but we publish one paper in Science of the Total Environment. In that, this is the first paper. We plan also several other papers for actually prepare a manuscript to send in the journals. And here you can see that we analyzed the main earthquake occurred November the 3rd, but we also, this earthquake had amplitude 5.4. But also we analyzed 3 additional earthquakes with magnitude larger than 4. One of them occurred at practically the same position like the main earthquake, and the other 2 earthquakes occurred at position G1. We consider G2. Sorry, we consider three signals. First is emitted from the Italy, second from the UK, and the third from the Germany. And focus, of course, was on the signal which is the closest to earthquake epicenter, and on the main earthquakes. So we use data recorded by upscale receiver station, and we, as I already said, we use a time sampling of 0.1 second. In these graphs, you can see variations of the recorded amplitudes from their smoothed values, and it is visible that amplitude noise. Here you can see quantity of this amplitude, recorded amplitude noise, that it is significantly lower in period from beginning from about 1 hour before the earthquake, and sometimes you will see later several hours after the earthquake with respect to the to its values before earthquake. These changes are recorded only for Italian signal. Here you can see, or you cannot see, I cannot see, but here this is Italian signal. For the other two signals, we didn't record some specific variations. This is a story for main earthquake. After that, we analyzed what happened in the case of other earthquakes. And here you can see that we also have reduction of noise amplitude for the earthquake with epicenter with very close, actually practically the same position like the main Kraljevo earthquake. It occurred on November 4th. For the other two earthquakes occurred at at position G2, we didn't record the changes. We wanted further to see what happened during October and November. We consider 1 hour in periods of around the time of Kraljevo earthquakes, and in this graph it is clear that we have significantly lower noise amplitude during November 3rd and also during November 9. We didn't know why, and for this reason we analyzed 3 whole days. The day when occurred Kraljevo earthquake, when occurred the second earthquake, for which we have noise amplitude reduction, and for the November 9th. And here you can see amplitude noise for these 3 days. It is important to say that in the within area around the ICV signal, many earthquakes are recorded during these 3 days, but only 11 of them had magnitude larger than 3. And here you can see times of the earthquakes with thick lines are indicate earthquakes with magnitude larger than 4, and for all of them we have reduction of the noise amplitude. Also, we recorded a noise reduction for 13 earthquake events. It is important to say that in a location near Kraljevo, 10 earthquakes are recorded with magnitude larger than 2.5, and for 8 of a total of 10 earthquakes near Kraljevo, we detected the noise amplitude reduction. That is 80%. Also, we recorded 15 noise reduction, and in 13 out of a total of 15, or 87%, these decreases can be related to earthquake events. It is very important also to say that our study shown that these reductions are not recorded only during nighttime. I forgot to say that the analyzed 4 earthquakes occurred during nighttime. But in this case, in this picture, you can see that the earthquakes occurred during daytime also can be connected with noise reduction. Now we have more events which we can connect with the considered changes in the amplitude and noise, but still we cannot say, okay, we have a new type of earthquake prediction, and this research is in progress still. At the end of the first part, I want to say something about the international network, European International Network INFREP. It has been established in 2009 and currently consists 9 receivers, 2 in Romania and Greece, and 1 in Italy, Austria, Portugal, Cyprus, and from the last year in Serbia. Here you can see what transmitter in points indicated by T are location of transmitters, and receivers are indicated by dark blue points. And here you can see path of transmitters which we consider. In the second part, we analyzed what happened with satellite signals in their propagation through the disturbed ionospheric region. So before I start with our study, I wanted to give some introduction. Namely, in this picture, you can see that signal propagation path is not a straight line. Namely, ionosphere practically induce changes in signal propagation path, and also these changes are recorded in a troposphere. In this table, you can see sources of signal delay and their values, and we can see that ionospheric delay provide practically the most important, the largest delay of satellite signals. Also, it is important to say that in the modeling of satellite signal propagation, delay of 1 centimeter is considered. It is important for our study. Now we will see how the ionospheric delay is calculated. Namely, we have 2 types of models. First is a single layer, and second is a multiple layer models. What that means? In the first case, we have models which use observational data from practically one altitude. However, in the other case, we have several observation from the several altitudes, which are practically input parameters in a model. Model consists of analytical expressions, and the results is calculated ionospheric delay. Of course, you know that the ionosphere is under permanent influences coming from the outer space, from the Earth's layers, and so on. And there are many disturbances which are not the same for whole ionosphere. For this reason, question is: are these expressions applicable during intensive disturbances, and also can local disturbances be important for ionospheric delay? Because we consider the D region. The D region is practically daytime lower ionospheric part, and we pay attention on this altitude domain from 50 to 90 kilometers. The most important perturber of the ionosphere, which are important for this story, is solar X-ray flare. Namely, this astrophysical event practically primarily disturb the lower ionosphere, and the changes in electron density in the D region can be significantly increased, maybe 1 or 2 orders of magnitude. But on the other side, changes in upper ionosphere are not visible. So we have information which are included in model from the upper ionosphere, and we have disturbances which occurred in the D region. Question is, can the perturbed low ionosphere, actually D region, sufficiently affect the GNSS and SAS signals so that the inclusion of the D region in the models become necessary for measurements? Here you can see SAR signals. That means SAR aperture radars signals, and these radars are satellite radars, and they are used for Earth observations. This research is still in progress, like in the first case, and also we publish one paper in IEEE Geoscience and Remote Sensing Letters. And here you can see a delay PD, for 3 frequencies, satellite frequencies of 1.2, 1.6, and 5.4 gigahertz. The influence of the region depends on these frequencies, and depends also on input angle of satellite in the D region. However, the main conclusion was related only to question can the disturbed D region affect propagation of satellite signals. In this graph, we in the left graph, we consider the one flare, and here you can see time axis, and here in the first upper 3 panels on y-axis is angle, and here the z-axis is practically a delay. You can see that this logarithm of this delay, and you can see that it can be about 10 centimeter. For the lowest frequency. Here you can see the maximum values of delay for angle of 70 degrees, and it can near not exactly 10 centimeter, but 7 or 8 centimeter. I repeat that 1 centimeter is included in calculation, so even we have not so intensive flare, their effects should be included in modeling of satellite signal propagation. Here in this graph, we analyzed the time of maximum solar X-ray flares, and we consider different maximum intensity of flares, and as you can see, this in the case, so we consider C class solar X-ray flares and M class solar X-ray flares, and for M5 solar X-ray flare class, our calculation showed that delay can be more than one meter, depending of incident angle. So main conclusion is that the disturbed perturbed the region can significantly affect the GNSS and SAR signals, and that practically this measurement should be included in calculation and modeling of signal delay during periods of intensive perturbation of the region induced by solar X-ray flares. I want to say that we consider flares until class of M5 because these flares practically don't disturb the upper ionosphere. The values, the larger, the most more intensive flares can affect the upper ionosphere, and this story should be modified because now we have some changes in input values in the program. And finally, summary. I want to say that presented studies open many questions which are important for research of natural disasters and practical application in the Earth observation and positioning, and this question related to research of influences of different parameters. They require more case studies, included other observation and databases, and also these questions relate to theoretical explanations and modeling. And thank you for your attention.
Thank you, Alexandra. Are there any questions? So let me pose my standard question.
Okay.
What do you find the most intriguing question in this context? What would be your most intriguing question in this context?
Intriguing question. I don't know. For me, the most interesting is precursor of earthquakes. It's the most important question, but we still need to provide some better statistical analysis.
So what is a specific point that you think we don't understand properly and that should be addressed most urgently?
Most urgently, it is important because we have variation occurred a few minutes before the earthquakes, less than 1 hour. That is important because the previous studies indicate the possibility for earthquakes several days before the earthquakes. And that could be important, but this is practically pilot study. It should be proceed.
Okay, just as a reminder, any further questions can also go into the chat. Anyone who wants to ask one right now? I don't see anyone. So in that case, let me thank Alexandra again.
Thank you.
We move on to our next speaker, who is Sasha Dujko, who will take us all the way to Titan.
Thank you very much for this nice introduction. First of all, I would like to thank the scientific committee and organizers of this meeting for inviting me and for giving me the opportunity to talk today under these extraordinary circumstances. My name is Sasha Dujko, and today I'm going to talk about electron transport, streamer propagation, and lightning in the atmosphere of Titan. This is the outline of my talk. In the introduction, I will discuss lightning as a planetary phenomenon. Then I will try to convince you that the atmosphere of Titan is a fantastic playground for plasma physicists. In the next part of my talk, I will discuss electron transport in Titan's atmosphere. I will briefly introduce you to the basic elements of a theory for solving the Boltzmann equation. And also I will introduce you to the details of our experimental setup, the so-called scanning drift tube apparatus, which has been recently developed with the aim of measuring electron transport data in hydrocarbons that play an important role in the atmosphere of Titan. In the last part of my talk, I will discuss streamers in the atmosphere of Titan using our fluid equation-based models and particle and cell Monte Carlo simulations of both positive and negative streamers. So what is lightning? Lightning is transient high current electrical discharge that occurs when large quantities of electric charge of opposite sign are separated over macroscopic distances. In the atmosphere of our planet, lightning strikes are actually a local phenomenon with global consequences as they transfer the huge amount of charge between Earth and the ionosphere. Likewise, ionization, lightning can dissociate nitrogen molecules, and therefore, most probably, lightning was playing very important role in the formation of amino acids and other prebiotic molecules in the atmosphere of early Earth. Lightning is a signature of atmospheric dynamics and cloud structure. It plays a very important role in the atmospheric chemistry. For example, in the atmosphere of our planet, lightning produces the huge amount of nitrogen oxides, lightning produces also various electromagnetic waves ranging from optical emission to high frequency radio emissions and very low frequency electromagnetic waves in the Whistler mode. Lightning has been detected in our solar system in the atmosphere of Jupiter, Saturn, Uranus, and Neptune. Lightning and thunderstorms are natural particle accelerators. So avalanches of high energy electrons are created in lightning, and these high energy electrons via Bremsstrahlung emit gamma photons. So the occurrence of gamma photons after lightning is the well-known phenomenon of terrestrial gamma ray flashes. These gamma photons in photonuclear reactions can produce high energy positron beams, and they can liberate neutrons and protons as well. So the presence of antimatter in the atmosphere of our planet after lightning was one of the most exciting discoveries in geophysics in the last, let's say, 10 years. In addition to high energy beams, lightning creates terrestrial luminous effects. So these are large optical events occurring at stratospheric and mesospheric altitudes. We can distinguish between red sprites, elves, blue jets, and gigantic jets and halos. Red sprites are essentially collections of streamers. The cause of elves is believed to be the heated electrons due to electromagnetic pulses after lightning, while blue jets and gigantic jets are beams of electrons that can excite air molecules. Okay, on this slide, I would like to show just one example of our recent simulations of production of gamma photons using a Monte Carlo simulation technique. So basically, our Monte Carlo code, which was initially developed for low energy electrons, has been extended and generalized to consider high energy electrons in the atmosphere of our planet. And as you can see, we are able to simulate runaway electrons and the occurrence of gamma photons. The production of gamma photons in our simulation is not, let's say, effective due to the fact that cross-section for Bremsstrahlung is significantly less comparing to other cross-sections for inelastic processes in the range of electron energies that have been considered in this simulation. Okay, Titan. Titan is certainly one of the most interesting objects in our solar system. Titan is the largest satellite of Saturn, and its atmosphere is primarily composed of nitrogen, methane, and trace amounts of hydrogen, hydrogen cyanide, and many hydrocarbons. And the presence of hydrocarbons and nitriles is explained as the results of photochemistry and charged particle chemistry. So the solar UV photons and energetic electrons from Saturn's magnetosphere dissociate molecular nitrogen and methane, forming new compounds that recombine and form new chemical compounds following the principle of minimal Gibbs free energy and maximal entropy. As shown on this slide, the atmosphere of Titan is rich with organic molecules. Actually, this is, excepting our planet, probably the most organic environment in our universe. Studies of electrical discharges are a good methodology for simulating the chemistry of Titan atmosphere. Low pressure discharges, including glow discharges and capacitively coupled radio frequency discharges, have been used to investigate the plasma-induced chemistry in the upper region of Titan's atmosphere. On the other hand, spark and streamer discharges were investigated in order to simulate lightning-induced events in Titan. It is very important to note here that spark and streamer discharges are particularly effective in production of acetylene, ethylene, and hydrogen cyanide. And exactly these molecules are more abundant than photochemistry models would predict. So one way to explain the vertical structure of Titan atmosphere is actually to assume the presence of lightning. So lightning produces energetic electrons which catalyze chemical reactions that would otherwise only occur at very high temperatures. On the other hand, no electromagnetic signatures of lightning were detected with either Voyager or Cassini flybys, including Huygens probe during its descent. So the question arises, does lightning occur or not in the atmosphere of Titan? So what do we know about lightning on Titan? In many independent studies, it has been shown that a methane molecule can condensate and undergo vertical motion. So this means that methane on Titan plays a similar role to that of water on our planet. Titan clouds made of methane should condensate at around 12 kilometers, while methane nitrogen condensate should freeze around 15 kilometers. Unlike our planet, charging of particle is not possible in the convective updraft as on our planet, due to the fact that charging interparticle rate is significantly less comparing to our atmosphere of our planet. So charging of particles by direct absorption of charges is more likely to occur. This can be actually understood if we take into account the fact that the electron density in the atmosphere of Titan is significantly higher than the electron density of in the atmosphere of our planet. Surface is expected to sufficiently conducting so that an image charge will form on the surface, and the lightning could take place either inside of the clouds or between a negative charge in the cloud and the positive charge on the ground. Okay, so what is the relation between lightning and streamers? Well, early stages of lightning are formed by streamers. So what are streamers? Streamers are thin channels of non-equilibrium plasmas that propagate in a medium with low or vanishing conductivity, such as neutral gas. We can distinguish between negative and positive streamers, and propagation of streamers require presence of initial free electrons, sufficiently high ambient electric field, and ambient gas as a source of new electrons. It is very difficult to model streamers. So using the language of plasma physics, streamers are non-linear, non-stationary, non-local, and non-hydrodynamic plasma phenomena. So we can use fluid equation-based models or particle and cell Monte Carlo simulations or eventually hybrid techniques to model streamer discharges. No matter which model we want to apply, the first step would be to consider scattering of electrons in the two most important gases in the atmosphere of Titan, and these are nitrogen and methane. So on this slide, we show our set of cross sections for electron scattering in nitrogen. And as you can see, all important processes are present, including those for elastic collisions, cross sections for rotational and vibrational excitations, cross sections for electronic excitations, and cross section for electronic impact ionization. On this slide, we show comparison between our theoretical calculations of electron transport coefficients in nitrogen and experimental measurements. And as you can see, these two sets of data agree very well, which is a clear sign that we will have a good balance of number of charged particles, momentum, and energy in our models of streamer discharges. On this slide, we show cross sections for electron scattering in methane. Okay, so to cut a long story short, so basically we have improved this set of cross section, the initial set of this set of cross sections by using the excitation coefficients for some individual channels of electronic excitations, and by doing so, we have actually improved the agreement between calculated values of the ionization coefficient with those measured in experiments. And this can be seen on this slide. So again, we have really good and really nice agreement between experimentally measured and theoretically calculated data. So this set of cross sections can be used as input to, for example, solve the Boltzmann equation. Speaking about the Boltzmann equation, so in this work we solve the Boltzmann equation, and we use numerical solutions of the Boltzmann equation to calculate all transport properties of interest. It is very difficult to solve the Boltzmann equation. So we apply the so-called moment method for solving the Boltzmann equation. So for us, the first step is to expand the phase space distribution function in terms of spherical harmonics. And by doing so, we actually describe the angular dependence of the distribution function velocity space. The second step for us under hydrodynamic conditions is to expand the moments of distribution function in terms of the powers of number density gradient operator. So this symbol G is just Nabla operator in spherical notation. In order to resolve the speed or energy dependencies, we expand the moments of distribution function in terms of Sonnino polynomials about a variety of Maxwellian weighted functions. Substitution of these expansions into the Boltzmann equation and integrating the Boltzmann equation velocity space converts the Boltzmann equation into one infinite system of differential equations for the moments. And then by truncating these summations for some finite values of these indices, and by discretizing this time derivative, we actually convert this system of differential equations to one large system of algebraic equations. The coefficient matrix of this system is sparse. It is actually quasi-free diagonal, and we have used some standard numerical techniques to tackle this large system of equations. As a result, we have the moments. From the knowledge of moments, we are able to calculate transport properties and distribution function itself. Speaking about transport coefficients, we can distinguish between the flux and bulk transport coefficients, and we need them as an input data to solve the system of fluid equations in order to simulate streamers in the atmosphere of Titan. Differences between these two sets of data are often significant, ranging from a few percent to a few orders of magnitude. So as an illustrative example on this slide, we show drift velocity as a function of the applied electric field for various nitrogen-oxygen mixtures. And as you can see, in the limit of very low values of V over N, and in the limit of the highest values of the applied electric field, we may observe differences between the flux and bulk drift velocities, which is a clear sign that care must be taken how to use data in modeling. Okay, Now I would like to say a few words about our experimental setup, the so-called scanning drift tube apparatus. This experiment has been developed by our colleagues from Wigner Research Institute in Budapest, and we are also playing creative role in the development of this experiment, and particularly in modeling. So the laser pulse falls down on the surface of a magnesium disc, which is used as a photoemitter. So this magnesium disc is mounted over the external surface of the cathode, which is connected to DC power supply to establish accelerating voltages for electrons that move towards the detector. So the detector consists of a grounded nickel mesh and another electrode, which is termed collector. So the detector is connected to step motor, so the distance between the detector and the cathode can be changed. So this experiment is unique because we are able to record the so-called swarm maps. So on this slide, we show our experimental data and simulation data for swarm maps. And as you can see, there is a really good agreement between experimental measurements and simulations. So basically, in this experiment, we measure current. So since the current can be related to electron density, then we are actually able to, by measuring the current, to extract transport data, including drift velocity, longitudinal diffusion coefficient, and effective ionization coefficient. I would like to show you just a few examples of our measurements. So on this slide, we show drift velocity as a function of the applied electric field for acetylene, ethylene, and ethane. And our experimental measurements are shown with these green stars. As you can see, there is a really nice agreement between experimental measurements, our experimental measurements, and theoretical calculations that have been performed using different sets of cross-sections.
You're pushing
on this slide. On this slide, we show the ionization coefficient as a function of the applied electric field. Again, as you can see, the agreement is very good between measurements and calculations. Okay, since we have transport coefficients for electrons, now it is time to say a few words about classical fluid model that has been used to model propagation of streamers in the atmosphere of Titan. So basically, we apply the so-called 1.5 dimensional classical fluid model. And this means that 1D continuity equations for electrons and ions are solved, while the Poisson equation for electric field induced by space charge effects are solved in 2D, assuming the homogeneous distribution of charge along radial direction. In this model, we use bulk data as an input to solve the system of fluid equations. However, sometimes it is not clear should we use bulk or flux data. And in order to resolve this issue, we have recently developed a so-called 1.5 dimensional corrected classical fluid model. So in this model, we use flux transport coefficients, while the source term is expanded, as you can see, in the powers of number density gradient operator. These expansion coefficients can be calculated using a Monte Carlo simulation technique. And on the right-hand side, we see the E over N variation of these expansion coefficients for various nitrogen methane mixtures. Okay, on this slide, we show electron transport coefficients in nitrogen methane mixtures. There are many interesting points in these profiles. Unfortunately, I don't have time to talk about that. So these data have been used as an input to solve the system of fluid equations. And on this slide, we investigate transition from an avalanche into a streamer. So if we assume that cloud altitude is around 20 kilometers, and this is a gas mixture which has been used in our calculations, and if we assume that the ambient electric field is 3 times higher than the breakdown electric field, as you can see, there is no transition from an avalanche into a streamer. So initial Gaussian just grows due to ionization. On the other hand, when electric field is 3.5 times higher than the breakdown electric field, as you can see, first signs of transition from an avalanche into a streamer are evident because the electric field is no more spatially homogeneous. When electric field is 4 times higher than the breakdown electric field, the full streamer is formed. So the electric field in the streamer interior is screened. As you can see, there is a field enhancement at the front of the streamer, and also the electron density decays in the streamer channel.
This is really
calculations have been performed for various nitrogen methane mixtures, and as you can see, we may observe much faster transition from an avalanche into a streamer when methane is added to nitrogen. Likewise, electron density and space charge effects are much higher for methane-dominated mixtures. Okay, just a few words about our particle in cell Monte Carlo simulations. So the initial distribution for electrons and ions are Gaussians with a peak density of 10 to the power of 19. So when the cloud electric field is 1.5 times higher than the breakdown electric field, as you can see, there is no avalanche to streamer transition. On the other hand, when the ambient electric field is 3.5 times higher than breakdown electric field, we may observe an avalanche to streamer transition. A double-headed streamer develops and propagates, and as you can see, the field enhancement for positive streamer is much more pronounced than for negative streamers. When electric field is 4.5 times higher than breakdown electric field, we may observe massive branching of both positive and negative streamers. So streamers always have the tendency to branch due to stochastic fluctuations of the electron density at the front of the streamer. On this slide, we show comparisons between streamers in nitrogen oxygen and nitrogen methane mixtures. So yes, this is the last slide. So as you can see, the transition from an avalanche into a streamer is much faster for nitrogen oxygen mixtures, and this could be explained by considering the ionization processes. So ionization is much more, let's say, intensive process for nitrogen oxygen mixtures. And as a consequence, photoionization is also a very efficient process for nitrogen oxygen mixtures. Conclusion. At first glance, it seems that streamer inception and the occurrence of lightning are not feasible in Titan atmosphere. Just to remind you, the breakdown electric field for Titan clouds is around 4.2 megavolt per meter, while the electric field in clouds is around 2 megavolt per meter. However, if we consider the case for our planet, where the ambient electric field in the thunderclouds is between 0.1 and 0.2 megavolt per meter, and the breakdown field, as you can see, is significantly higher, almost an order of magnitude. According to these numbers, there should not be lightning in the atmosphere of our planet. And as we all know, lightning occurs in the atmosphere of our planet. Actually, the flashing rate is between 50 and 100 lightning strikes per second. So, since the ambient electric field is let's say, is less than breakdown electric field for a factor of 2, lightning is most probably is possible on Titan. Okay, future work, simulations of streamers and production of prebiotic molecules in the atmosphere of early Earth. This is a work in progress. Simulation of streamers in the atmosphere of exoplanets. So exolightning is a new and developing area of research. And simulations of runaway electrons, emissions of X-rays and gamma photons are also in our focus. Thank you for your attention.
Thank you, Sasha. Talking about future work, what would be your future question?
Future question? Oh, that's a good question. Okay, well, At this moment, we are working on simulations of streamers and production of prebiotic molecules. So it would be really nice to see how actually electrical discharges, which should be modeled in a self-consistent way, how these discharges can produce prebiotic molecules, including amino acids. So that would be really, really, let's say, a holy grail of this research.
That sounds interesting indeed.
Of course, exolightning. Exolightning is very exciting area of research. So we are waiting for the first results of James Webb telescope, and then we would be able to model the presence of lightning in the atmosphere of these exoplanets.
So I should refer to further questions to the chat. Thanks, Sasha, again. And then we should move on to take a ride on interstellar travel with Dragan Lukic. Dragan, are you there?
Hello, Dragan. Can you hear us? Could you unmute yourself, please? Vladimir, can you send the invitation for...
I sent.
Ah, okay, thank you. Can you send through the chat also, please? Hello, Dragan. We cannot hear you. Could you unmute yourself? Okay. If not, we will move to the next talk and then we will get back to Dragan. Is it okay, Martin?
It's okay with me. The question is whether it's okay with Vladimir. So
Vladimir,
the
is
second
it okay?
speaker would be Vladimir Dechkovic.
Yes, it's totally okay.
Okay.
Thank you.
So in that case, the floor is yours.
Okay. Is it okay with the presentation?
Yeah, looks very good.
Thank you. Good afternoon, dear colleagues, and I want to thank to the scientific committee for the opportunity to present our work. This is mainly progress report, and I will be very brief, shorter than 20 minutes. So colleague Lukic will have enough time to present his talk. So the goal of this presentation is mainly to inform public with our activities and possibilities and opportunities in Europlanet consortium. What is Europlanet Society? It is an organization which promotes the advancement of European planetary science and related fields. You can see information about the organization and activity of this society, and it can be found on the web address www.europlanet-society.org. So this society is very, very interesting and big. It has an executive board. Maybe someone knows, maybe not. The president is Sir Nigel Mason. He's president of the Europlanet. And interesting thing is that he attended our conference in August, and that was very important for us. Something about Europlanet history. First, Europlanet links research institutions and companies active in planetary research in Europe and around the world. Planetary science covers the study of our solar system and those around other stars. It can be an interdisciplinary field of research that covers astronomy, geophysics, data science, robotics, exploration of other planets, and etc. Of course, search of extraterrestrial life. Since 2005, Europlanet has provided Europe planetary science community with a platform to exchange ideas and personnel, share research topics and facilities, define key science goals for the future, and engage stakeholders and policymakers of European citizens with planetary science. At 2005 to 2009, European Planetary Network, Europlanet, received €2 million under framework 6 FP6 project for networking activities to build a strong community for European planetary science through meetings, workshops, and develop synergies between space missions and ground-based observations, and laid the foundation for a virtual planetary observatory. From 2008 to 2012, Europlanet received €6 million under Framework 7 Integrated Infrastructure Initiative program to develop a distributed research infrastructure to enable researchers to access state-of-the-art laboratory facilities, planetary analog field sites, and virtual access facilities. Between 2015 and 2019, and after that, from 2020 to future 2024, the Europe Planet get fund from Horizon project, Horizon 2020. So Europlanet provides transnational access to 24 laboratories in Europe and 5 field sites, virtual access to services and tools, network activities to support the community and provide a rapid response observation to support planetary missions. And most important, early career research support. And this link is very interesting and for young researchers. The important thing in Europlanet society is annual meeting every year. It happens, and this year, due to the situation with the pandemic, was virtual. We had a representative at the Congress. That is an important thing. And you can see down here, every year in different country, and a lot of attendees, almost 2,000 attendees in last 2 or 3 years. First Congress was in 2006, Germany, Berlin. Europlanet Society members are spread into 10 regional hubs. You can see from Benelux hub to Central Europe. Some countries have their own hubs, some not. Our hub is Southeast hub with Bulgaria, Croatia, Cyprus, Greece, Romania, and Serbia. So you can see on this website the details about this Southeast hub. And mainly the main topic of this progress report is to show our activities in this hub in Europlanet. So we have 20 members from 7 institutions. We are participants in Europlanet meetings. We organize our own Serbia Europlanet group meetings. It is almost annual meeting for Serbian scientists. And it is very interesting and very good for our science. We organize 2 Europlanet meetings or workshops. First, training school was in 2018 in Petnica Science Center, Serbia, and with the title Geology and Geophysics of the Solar System Bodies. The topical sessions include solar system dynamics, asteroids and small bodies, planetary geology, planetary surface processes, planetary interior, space exploration, meteors and meteorites. The scientific organizers, the main person was Anna Chernok with Katarina Miljković and Matija Čuk. The aim of this workshop was for students and undergraduate and master students to get some experience and to learn something. In total, there were 14 lecturers, 7 female and 7 male. But from Serbia, only one attendees, that was Bojan Novaković. All other were abroad. So the next workshop we organized in last year in May with the title Integration of Satellite and Ground-Based Observation and Multidisciplinary in Research and Prediction of Different Types of Hazards in Solar System. It is a very long title, but very informative. This event was supported by Europlanet 2020 Horizon project and by our ministry. The total number of participants was 33. Number of female participants 8 and male 25. The participants are from different countries, from Serbia, Bulgaria, Croatia, Greece, Hungary, Italy, Russia, Ukraine, and Serbia. You can see on this picture a lot of known and unknown faces. This is Professor Milan Radovanović, director of the Geological Institute, Jovan Cvić, Aleksandra Nina, Milan Dimitrijević, Luka Popović, Natasha Todorović. You can see Bratislav Marinković, he is our MC, main in the cost actions. This is Peđa Jovanović and Anđelka Kovačević and other people. So the whole atmosphere was very pleasant, and we discussed a lot of about our future work and about possible cooperation in some projects and etc. The venue and both of workshop were Petnica Science Center, very beautiful and very beautiful place. After workshop, several established cooperation of scientists from different countries happened. We joined several lot of our scientists joined Cost Action Electronet, atmospheric electricity network coupling with the Earth system, climate and biological system. We include Institute of Physics Belgrade in INFREP, International Network for Frontier Research on Earthquake Precursors, and we published a lot of papers. This is just a slide of this INFREP in Belgrade, and you can see this INFREP network currently consists of 9 receivers located in Romania, Greece, Italy, Cyprus, Austria, Portugal, Serbia, and other countries. We had 2 annual meetings. First meeting in Astronomical Observatory in June 2019, and the second one at the Institute of Physics on February 2020. I would not go into the details about activities of the members. We have an annual report, so on our website you can read our activities and get information about Serbian Europlanet group. You are welcome to join Europlanet through Serbian Europlanet group, and thank you for your attention. That's all from me.
Thank you, Vladimir.
Thank you.
Are there questions? So I assume you already started preparing for my standard question, which will come in a modified version. So what would you consider the most significant gap that is worth addressing?
But the most significant is how to get some money and project in European Union, and that is the main thing.
Any further thoughts?
Just the main thing is to inform the people about the existence of this possibility, and for young scientists to join the planetary science and to explore in some virtual sites and some laboratories, or exchange some knowledge and that thing.
I mean, something that I've always found important is if you want to engage young scientists, you know, it helps if you trust in them and, you know, treat them as equals or not inferior to yourself. That can make a huge difference.
Yes, that is good. That is good. And I agree totally.
So there's a question on the chat.
Yeah.
Which asks, does Europlanet still support visits to laboratories?
Can you repeat? I can't find this.
Question is, does Europlanet still support visits to laboratories?
Yes, but it depends on the institutions. So generally, yes, but you have to ask that laboratory, is it possible to go there? So generally, yes.
That sounds good. Okay. If there are no further questions, then I would like to thank Vladimir again. And then let's see whether we can rebook our interstellar travel and call on Dragan Lukic again.
Hello, Dragan.
Oh,
Great, we can hear you.
let me try, start with my presentation.
Yes, of course.
Just a second, please. Okay. Let me start. Okay. This will be presentations about.
Just a moment, please. This is not from the organizers. We cannot see your presentation. So just open the presentation.
I opened.
And then click share the screen button. This is green button in your Zoom.
Share the screen, okay?
You will see several panels and click the panel.
Okay, just a second. Is this?
Yes.
Can you see it now?
We can see it now. Great.
Okay.
Yes, we can see it now.
Just a second, please. But now, okay, now starts. Okay.
Looks good. Yeah, thank you.
We will discuss this in this presentation, the most recent projects for sending interstellar ships, but we are not interested in interstellar. We are interested in regions on the border of our solar system. It is area between 100 to 400 or 500 astronomical units from Earth. To get there, we need at least 20 astronomical units per year speed. To be able to get for in lifetime of one scientist. This is not rocket science, it's spaceship science. We don't use propellant. Solar sails use photon pressure on thin light weight reflective sheets to produce thrust. Sails can now open these regions of our solar systems, which are not really accessible to us. We have now only two probes entering that region, and we are getting a lot of results from there. Actually, maybe one day we will be able to transfer to some close passing by star, coming toward the Earth closer than 1 parsec. Last such event was like 70,000 years ago, most probably. The most advanced solar sail system now is contracted by NASA. It was done by a project in 2002, and this technology is done by Lagarda and Attica Space System. Unfortunately, solar sail Sun Jammer, which is thick 5 micrometers, is cancelled in 2014. Not only Americans, but also Chinese do it. They're doing testing 8 by 8 meters and testing 100 by 160 meters solar sails for 3 asteroids, for visiting 3 asteroids in asteroid belts. They tested Kapton with a weight of 12 grams per square meter. And they tested the polyamide for 8 with the thickness of 8 micrometers. Present sail thickness, the best one is 2 micrometers from European Space Agency. They're using metallized plastic films thick around 2 micrometers. NASA has technology for 2.5 micrometers aluminized plastic. In papers, we can find fantastic thickness of the graphene layer. Single graphene layer, like the space with the space of 100,000 square meters, covered by 7 grams of highly reflective material, which is not possible. Avram Loeb, with the breakthrough initiative from the Harvard Smithsonian, they plan for 15 layers silver or titanium dioxide, or Lublin. They are planning for just 1 micrometer, which is not so bad. Present solar cells are very hard job. The problem is how to fix it, how to make the source, and how to make the seams not falling apart during the sun jammer has approximately half of its weight just for adhesive tape applied to the seams on their seams. Sun jammer is cancelled, and it's 45. Its weight is 45 grams per meter. Light sail is launched, and it shows some acceleration. Now, next mission is a near-Earth asteroid Scout. It's planned, and it should be launched in 2021. Pure graphene, which is now in many papers for solar cell, is actually very bad material for solar cells. Its reflectivity is almost 0. We cannot apply that material alone. We need to apply it with some other combinations. For example, molybdenite, or to use it just as for its incredible strength, not its incredible reflectivity. Its reflectivity is actually very bad. Let me start with different types of solar cells in literature. One of the first paper was by the Robert Forward. Now he's late. It was 1,000 kilograms probe with cells of diameter 3.6 kilometers. He planned to apply from 500 million tons Fresnel lens in a solar orbit. It was really tremendous Fresnel lens. It was supposed to be like 100 kilometers diameter. He had even the idea how to return the space probe from that solar extrasolar system. But whole economy of that project was really bad. For 65 gigawatt laser, you need to apply, for example, for 4 years power of such laser, you need to spend like 114 billions of dollars. And if we assume that the efficiency of producing the laser light is like one third, it is like 340 millions for just energy to supply for 4 years. The travel to the next, the closest star, it was assumed that it will get there in 40 years. Just for energy, it's like three trillions of dollars. And if we add just $1,000, 1,000 billion of dollars for launching that huge amount of plastics needed to produce Fresnel lens, it is like 4 trillions. There is no government which could spend so much money for sending just one space probe for 40 years. Next, in the last 5 years, they came with a lot of different projects. One is from the Harvard-Smithsonian laboratory. That there's this breakthrough space initiative is run by the professor Avram Loeb, and their paper, they claim they main besides lasers, which they do not have, the biggest expenses is 4 hours of 100 gigawatts, applying 100 gigawatts of electrical energy for 4 hours to propel small several grams weight of space probe, which is really small probe to get any message back to the Earth. Even they are not good with the economics. They claim that generating the 100 gigawatts of class power is very small problem, and it is very cheap. It's less than one dime per kilowatt, but you cannot really make 100 gigawatts power stations somewhere in the mountains close to such thing, such launch space. It is not possible. One other solution is to bring the whole energy in batteries, but in batteries its relative low cost is $12,000 per kilowatt hour, which amount to 360 billions of dollars for just 4 hours. 4 hours. Even if that is not complete calculations. A later version of David Kipping, they included divergence of laser beams, and needed power is 500 gigawatts. And it is like 1.8 thousand billions of dollars, which is really not feasible. One way to fight with this is to send several hundred probes per one system, which is a little bit better than Forward's proposal. Only problem is that we don't have small radioisotope thermoelectric generators, which will last so much time. For like 50 years need to go there, and most of our radio thermoelectric generators are not several grams. They are several hundred of several tens of kilograms. We cannot send anything there which cannot really operate and send a message back. Other solution was solar sail for Alpha Centauri. It was done by René Heller and Michael Hipke from Max Planck Institute for the Astrophysics. But actually, they made big mistakes. They really underestimated the thickness of reflective coating. For example, they claim it will be 7 grams per 100,000 square meters, but single atom of helium absorbed per one hexagonal of atoms of carbon atoms of graphene, it will be 12 grams per 10 to 5 square meters. We try to make this solar cell with non-diverging laser beams. We are trying to avoid these problems of other groups, but we are not really lucky with that. Our concept is to try to non-diverging laser beams. We will have much larger acceleration range. It will be like 4 to 5 times larger. That means that our weight can be or larger, or our sail should be smaller. How to produce such beams? We can produce basal beams with diodes. We just do not have technology for solar-driven. We now do not have technology for solar-driven laser diodes, but we have solar-driven laser. We have technology for. We have solar-driven neodymium YAG lasers, and also we have technology now for to be inside the Mercury orbit. Solar orbiter perihelion. Perihelion is 0.3 astronomical units. Solar Parker probe is 0.4 astronomical units, closest approach to the sun. Now we have technology to solve heating of the sun. We have other problems. Our big other problem is launch cost to the Mercury orbit. United Launch Association Delta IV rockets cost like $140 million, but with some additional booster needed to go to Mercury orbit, it can be up to $450 million. It is mass approximately of 650 kilograms, which means that best price is 4 kilograms per $1 million. Falcon 9 will be cheaper. Rocket of private company would be cheaper. Solar collectors, we cannot make it really now less than 100 grams per square meter, which give us the price for just for collected solar radiation of 52 kilowatts per square meter. Its price is like $20 per watt. It is it is not laser light. It is just collected solar light. We have really 5% effective transformation from solar light to laser light with the neodymium YAG lasers, which things that will have like $100 per watt. What we can do, we can lower mass of our collectors at least 20 grams per square meter. And other big savings would be collecting all producers on Earth to produce rockets for this endeavor. It would be like 1/10 of this price. We have producers from United States, from Europe, Russia, and China. I don't know, is it really politically possible to get all four to work on this project? But at least there is a chance. With that, we can, with all this, we can go up to approximately $1 per watt, but we need a lot of watts to go there. That will be all. Thank you for your attention.
Thank you, Dragan. Anyone who wants to ask a question, you can raise your hand, you can write in the chat. And in the meantime, I ask my standard question. Where do you see the most significant gap or obstacle?
The most significant gap and obstacle is producing the very thin solar sail. I'm proposing to use additional manufacturing to print such sails. Because we have technologies now to print big area to be very thin. We can produce all these adhesives and tapes which we need now. We can produce it now with the stronger, thicker part of the solar sail. But this technology needs to be advanced, really. This is forefront of printing of solar sails will be new technology. And we can make really addition to the aerogel, graphene aerogel, to make addition of different dopants, which will make our solar sail really reflective. The problem is solar cell is you need to apply all new layers, different layers to get the different functionality. We now want to produce just single layer with really good functionality, with good reflectance and really good stretching resistance.
Okay, further questions? If that is not the case, then I thank Dragan again. In fact, is Sohan still around?
I have a question. Can you hear me?
Yes, I can hear you.
Okay, I would like to ask Dragan, I understand that the target of your mission is the region in between 100 and 400 astronomical units and so on. Yes. But what is the motivation for such a mission? Is it a technological mission or there are scientific goals? And if there are scientific goals, what are the principal goals?
The principal goals is scientific, to research all parts of our solar systems. We sent 2 probes, but we need to send much more probes to try to better understand our heliopause pause and bow shock and everything.
Okay, okay. Yes, these are the open questions. Yes, and thank you.
We cannot really ask anyone to live 150 years to go there. You know, it's too impossible still. I hope it will be better in the future.
Okay, thank you.
Which actually raises the interesting question on how long could humans live in principle?
I think like 120 years.
Yeah, which is what most of people now tend towards.
Yeah, it tends like half.
Yeah.
In most of the countries, really sufficient way is to really live this full life up to 65 years, not less, not.
It's not the question of living longer. It's really the question of can we survive in space, because there are proteins do not fold properly in space, especially those that are concerned with the mitochondria. You'd be.
I don't think we will go there. I think that we will send just probes there. I don't really believe that we will go there. We will send the probes. No, I don't believe.
Probably, yeah, that's probably more like it. Yeah. It's not possible, but we don't. I think it'll be 1,000 years before mankind could ever set.
In 2000, the NASA even stopped working on the so-called generation ships. I was there in the United States, and I read that NASA in 2000 they stopped talking about generation ships. Even if you send something weight of Nimitz aircraft carrier, you will not have enough food, energy, and anything to survive such long period. You know, it is just not possible. It's possible just to send the probe somewhere. And I have idea how to send samples of our biological life out there, but it will be next paper.
Do you have an opinion of exploring space by means of microsatellites rather than sending big things?
No. I just want to send the examples of life from the Earth to other possible exoplanets. But I am not sure that we will hit it, okay?
Because one question we were coming about in a recent discussion was, if you can send one probe somewhere, where would you send it?
We cannot send it anywhere with enough precision. Even with the Gaia data, we don't have enough precision to send something which will go there for 20 or 40,000 years. So we will miss that planet or exoplanet or whole planetary system. We can just send by whole chance, because we don't have enough precision of measuring movements of other stars. We don't know where it will be in 20,000 or 40,000 years, how much time we need to get there.
Thanks. That's very, very good point that was missing in our discussion.
Just 1 second, Martin, one more thing.
Yes.
If you send small nano robot out there into space, by the time it reaches its target, even the nearest Alpha Centauri, what would actually happen is that these particles, they will gather water all the way to Alpha Centauri. By the time it gets there, it will be probably size of Mount Everest, the spacecraft you sent out, because of the stickiness of water. The most sticky thing in the universe is water.
Yeah, I knew. There is a whole part of astrophysics working with small particles of water in interstellar clouds. But I don't want to send any machine. I want to just send samples of life from Earth, protected from radiation.
Oh, I see what you mean.
Protected, but you will see the paper, okay? I will send you a paper one.
Yeah,
before I will send you paper before I submit it, okay?
Yeah, but thank you.
Going back to life in outer space, there was a question on the chat for Sohan, which was, can the actions of synthesis of more complex polymeric compounds occur somewhere in space except planets? Could it be comets or something else?
Well, they have identified at least a 13 carbon chain long polymer. But if you are thinking about, because Oleg Kotzyblanko already asked me that question, if you were thinking about putting together chains of amino acids or chains of nucleotide, it is not possible. You can't do that because that's a particular type of chemistry, you know. So it's not possible to find these molecules that are friendly to life being made in space. But what is good thing is that the very last slide that I showed, where Cooper 2011 did this, they collected this data, small molecules. Now, all these small molecules are very important in the formation of life. There are about 250 molecules altogether, you know. So from that point of view, there is an idea being floated by a guy called Stewart, John Stewart, I think his name is, but definitely his second name is Stewart. He puts forward the idea, what's called managed metabolism hypothesis. So he relished the idea of small molecules. But other than that, there's no way that you'd get organized, which is what they are. The biological polymers are organized, and also there's a question of homochirality comes in as well.
Can I tell you something? That's for this reason, I think that not black smokers from the bottom of oceans are not place where life started on Earth. I think that the problem where we can get enough concentration of biomolecules is the hydro vents on Earth, not on soil, not under the water.
Look,
the biggest problem is the concentration of biological precursors of biological for making the vesicles and making compounds inside it. The biggest problem is concentration, and that concentration we can have it inside the hydrothermal vents on Earth, on soil, not under the water.
I understand where you're coming from. Concentration isn't the only factor. What's important, equally important, if not more, is amplification of molecules. So you need rate of formation of molecules greater than the destruction rate.
Of course.
Do you see what I mean? Rate of formation of polymers
Yes.
greater than the destruction rate.
But the biggest, I think the problem is where the vesicles could start their, they were the biggest amplifier of biological process vesicles. And you cannot have enough vesicles in the hot water on the bottom of ocean. You can have it in the hot water on earth, on soil.
This gets us into an interesting discussion, which I fear we won't come up with a definite
Of course,
conclusion
no.
right now. So I would just like to give the opportunity for one last question to Dragan, which is long time ago, there was an idea of using interstellar masers to send signals and communicate with other civilizations. Are there any idea of using bright masers to help push sails in some way?
Yes, there were such projects, and they made it as an amplifier. Amplifiers for masers were cheaper in 70s, but not now. No, they were cheaper in 70s than now. There are such papers in literature.
Yes, I remember that. And so my idea is, could we use interstellar masers in some way?
Well, I don't know. I told you, I'm not aiming for the stars. I'm just aiming for the shock zones around the solar system. So I will present my paper for interstellar travel, but not with the lasers. Okay.
So in the hope that we found some answers to the questions that were posed, and in the hope that we didn't find questions to some of the answers that were posed, that means that some interesting questions still remain. Yes. Let me draw this session to a close and thank all speakers of this session again, without which the session wouldn't have been there. And let me hand back to the Master of Ceremonies.
Thank you, Martin. Thank you all presenters. Thank you all participants for this wonderful discussion and session. And we should now move to the next section,